Okay, this is really very high-tech stuff, so I'm still struggling to work with it. This is course 7700, an elective, graduate elective on computational transport phenomena. Can you guys see in the back? Not quite. So here is a quick outline of what the course is about and how the assessment will take place. And I am trying to do something, as I said, to use technology to teach over the internet, but obviously you saw that it failed the first lecture itself. But I will be tinkering with it during the course, and I want you to kind of bear with me as we figure this out. The course is going to cover numerical methods for solving engineering problems. Okay? So we will cover a whole range of topics, starting with physical models, which is what I'm going to do today, moving on to review of linear algebra, nonlinear dynamics, functional approximations, and then differential equations, ordinary differential equations, partial differential equations, by a variety of methods. The methods will include finite difference, finite volume, finite element, etc. So it's an introduction in that sense, but it is a graduate level introductory course. So we do assume that you will have taken all the core courses in engineering. That will be a course on differential equations, a course on mathematical modeling, some sort of a course on computer programming, because you cannot do numerical method without having a knowledge of the computer programming. Now, I'm not going to require that you use any specific language. I will illustrate problems with MATLAB. MATLAB is a good environment. How many of you have not used MATLAB before? And 11, I think there were 16 registered. Are you willing to put the extra effort to learn MATLAB? You will, okay. There are material online, even I have put some, so you need to, there's a course that I taught last term for undergraduate level, MATLAB. So that set of about 10 lectures or so are on YouTube, so you can listen to that. And the other thing is my co-instructor in this course is going to be Mrinal. Mrinal, show up your so that people know. And Mrinal is going to be preparing a set of problems and illustrating them with COMSOL. Okay, in COMSOL you don't really need to program, but you need to understand the physics, you need to understand the numerics, and that's what I'm going to be focusing on the lectures. And what Mrinal will do is either during the lecture hour, good morning, come in, or from his office record illustrations of how do you solve a variety of problems using COMSOL. But I think it is important that you do both with MATLAB and COMSOL. So there will be some assignments that will be done with MATLAB and others with COMSOL. So the idea is by the time you are finished with the course, you should be able to solve a variety of engineering problems, whether it's algebraic or differential equations, using a variety of tools, software tools, computational tools, and understand the results that are produced. So I have an extensive list of bibliography. These are all books dealing with computational aspects, transport phenomena aspects, mathematical modeling aspects, etc. When I take a material from a particular book, I will tell you the references for that. Okay? And the next important part is the assessment. So there will be a number of assignments. Some of them may be long and challenging, so the number may be limited to 5 or 6 or so. They will be worth about 25%. And then there is going to be a project, because it's a fairly small class. And the project will involve basically not an extensive literature search or anything, but I will give you one paper that has solved a problem using COMSOL or Fluent or whatever, and I will say go ahead and reproduce those results. Okay, and then there will be a presentation to the class. So 50% of the assessment is going to be based on that. Okay, and I will try to give this paper out for each one of you probably towards the end of this month, in about 2 weeks' time, and you will have the whole term to work on it. And you are always welcome to talk to me or Mrinal if you need help in figuring out what to do. So that's like doing a mini research project on a problem that has already been done. So the path is clear for you. You just have to jump through the hoops to get to the result. And there will be an oral exam. There will be no written exam in this one. So there will be an oral exam for 30 minutes each that I will schedule at the end of the course. And maximum 30 minutes. It may not last 30 minutes. And it depends on whether I get a sense for what you have done, you have understood. Okay? And it could be based on the lectures that we cover in the class, probing you whether you understood certain concept, and also on your project. Okay? So what did the guy do and how did you understand it, interpret it, defend basically what you have done in the project and in your presentation. Okay? Any questions on that? No? Okay. So I will put material on Moodle and maybe on Google Docs as well, because the guys from outside cannot access Moodle. They don't have a user ID, so I need to figure that out. And I'll put a set of lecture notes as well on that, and then all the assignments, solutions, etc. will be there. And the videos of this lecture and examples that Mrinal is going to do, we will create a playlist on YouTube, and we will put all those material there with link to Moodle. Now I need to figure out, can you guys read any of these at the back? Probably not. Need to figure out how to expand this. Okay. Let me just talk about the concept of what a simulator does. Okay, there are big companies like ANSYS, COMSOL, StarCD, etc. They claim basically that they can simulate very complicated engineering problems. So the way that traditionally chemical engineers, I'm a chemical engineer, so I'm going to draw examples from there. How many of you are not, are from outside chemical engineering? 1, 2, okay, 3. Which department are you from? Petroleum. And you? Petroleum. Okay. We are close enough. Chemical and petroleum are close enough. So you should be able to understand the examples that I'll be talking about. Okay. So we try to, traditionally we have been designing it basically intuitively. Okay. What does that mean? Let's take a distillation column as an example. Okay. I know that if I have a feed of mixtures and I want to separate them, and the mixtures have different boiling points, I can exploit that difference and set up a temperature gradient in a column, and then I can draw the products, because each particular level or a stage will have a certain temperature and only certain compositions can live in the liquid phase, for example. So I can separate the light ends to the top and the heavy ends to the bottom. And then thermodynamics came in to help us quantify, okay, how many stages do I need. Of course, fluid mechanics is always there, because what we are doing is we are mixing, heating up, vaporizing. There are two phases. If you take reservoir engineering in petroleum engineering, you also have a crude with dissolved gases possibly, and as you are producing it, it has water in it. You are trying to separate that. Okay, so we often deal with multi-phase flow situations. Okay, so and we do that experiments. We just build the thing and see whether it works. That's a pilot scale approach to design and scale up. Now, with these advanced simulators like Aspen and ISIS at one scale, and then Fluent and StarCD at the COMSOL at another scale, we can actually, you can come and sit here. I'm not going to bite you. The front seats are fine. And you can actually have a better view of what's on the screen than in the back, I think. Okay, I'm not able to blow this up, I don't see an icon anywhere to. I just need to learn how to use the software. I haven't done my homework yet. Full screen, let's try that. Still, it's not very good. So the pilot plant approach, an empirical approach to the design of process equipment, was the traditional way, starting from early 1900s all the way to 30s, 40s, and then the mathematics of it was developed for design, and but these were often algebraic equations, graphical methods that were developed. McCabe-Thiele method as an example, and it's only around 2000 computers became powerful enough that we could solve fairly complex problems in great detail. And this course is about that level of modeling with some rigor. So for us, the conceptual overview of modeling says that there is a physical world that I'm trying to understand, and that physical world is different for different people. For physicists, it is essentially maybe on the astrophysical level, galaxies, and on the particle physics levels, muons and quarks, and what is the most recent one that was discovered? Higgs boson, right? So the physical world is different for different people, but the approach to that is essentially the same. Okay? For us, chemical engineers, it is a chemical process plant. Okay, a distillation column, an absorption column. For petroleum engineers, it is, if you're downhole, you're looking at reservoir, moving the fluids through a porous media. And if you produced it on the surface facilities, you are basically talking about similar equipment that chemical engineers do. So we observe that, we watch that, and then we ask, how can we build models to represent them? So a model is, suppose it could be a physical model or it could be a mathematical model. A physical model will be a miniaturized version of what we are looking at. Petroleum engineers do that often. Their scale model, displacement tests and stuff like that. So mathematical model is about representing the process mathematically so that we can solve and be able to predict what the performance of that particular physical equipment is going to be. So there are two fundamental approaches that we can use. One is we do experiments on the physical system. We build it and do experiments and plot the data. Okay? And once we plot the data, we try to fit through an empirical curve fitting. A good example from chemical engineering will be reaction rate processes. So if you want to look at how fast a particular reaction is going, you mix the two reactants and take samples over a period of time in a batch setup, and you plot concentration versus time. Right here. Okay, C versus time. And you get a curve like that, for example. One of the reactants is decreasing with time. That data is obtained as discrete data points, and then you try to fit a curve through that. And from that you get a rate. The slope of that is dc dt, the rate at which the concentration is changing. You relate that to the rate of reaction. Okay? So if you want to get models for rate of reaction, you can do experiments and do curve fitting. Same thing happens with the PVT behavior. Okay? So the earliest observation on that is, how is pressure, volume, temperature related? Charles' law and Boyle's law, for example. And you put an equation together, which is PV equals nRT in ideal gas, and then you find that that doesn't work, and then you expand on it and build more sophisticated models like Penn-Robinson equation of state, Verrill equations of state, etc. The other approach is to look at conservation laws, okay? Conservation of mass, conservation of momentum, conservation of energy, and do thought experiments. How was the conservation of momentum obtained by Newton? F equals ma. How did he come up with that? Just thought experiments, right? Observations of, the classic story is observing the falling apple, thinking about it, and then introducing concepts like acceleration, like inertia, and stuff like that, like force, and come up with a model that captures that process, and so it can predict how fast an apple will fall or how long will it take. So you can pose a lot of these questions. So that's another approach, thought experiments, conceptual, and those are much more widely applicable. Okay? Whereas these experimentally based ones are applicable only for those close class of experiments. But we need to put these together Okay, so construct mass and energy balance equations, construct phenomenological models, empirical models, PV equals nRT, etc., and put them all together to get a mathematical model, which is a comprehensive model. And that's the kind of thing that you'll be doing in a project. When I give you a paper, it will contain a model for a particular system that they're going to analyze. And that will have elements of all these, conservation-based equations, empirical-based equations, etc. And you need to have a complete representation, but it is only an approximate representation. So that's the first degree of approximation that we must be aware of, so that when we are trying to predict, we know that it is not exactly the real world. Even f equals ma is not real if you're dealing with relativistic effects, for example. Okay? So there is always a degree of approximation and that we should be aware of. Okay? And I will get better at this. Come on. There. Okay. This works. How do I go? There was something in the bottom that I wanted to get, but three guys still sitting there. I don't know what. They cannot hear me. Page down doesn't work. Does this work? No. So what is underneath is the link between the mathematical model and the numerical model. That's another approximation that we need to be aware of. In fact, the course is going to focus on that link, not on this link of representing the physical world in terms of the mathematical model, but getting the mathematical model, which is so complicated that we have to use computers to solve them. So there are approximations involved in there that we need to understand. Okay, now we can see it. Okay. So the mathematical model, we need to classify it into various groups so that we have a feel for what type of tools that we need to develop to get the numerical solution to that. As a practicing engineer, what you will be dealing with is set of simulators like COMSOL, Aspen. These are all examples of it. And all you will be doing is putting some input, you're going to get some output, and you're going to interpret that output and design your systems or analyze the performance of it. But in order to use this intelligently, we need to understand what is the mathematical model and what is its character so that we know what type of tools are used in COMSOL or in MATLAB. Okay? So I'm going to give you an example of each type of model that we are going to look at in this course. But just to give you a classification, the first classification will be between linear and nonlinear models. Okay? So how many of you have an understanding of what that difference is? Can anybody articulate what you understand by linear model versus nonlinear model? What is the key feature that you would look for in a model that will tell you whether it's linear or nonlinear? What does human mind do? It always assumes the simplest linear model, right? Going back to the flat Earth model. So at one time we used to think that the Earth was flat because our observation went only so far. Okay, and so when we measure any temperature versus, concentration versus time, we try to put a straight line through that. Okay, so a linear model basically, in algebraic terms, it's y equals mx plus c. It's an equation for a straight line, mathematical representation of one variable x that varies linearly with another variable y. Okay, and the rate would be the m, the slope. And if you're dealing with differential equations, then how do you know that particular model is linear or nonlinear? You should be able to identify which is the unknown that you're solving for in the model equation that you have. And that unknown, does it appear by itself in a linear fashion, or does it appear as, suppose u is your unknown in a particular model, stands for some velocity or whatever. So if you have e to the power u, or sine square u, or sine u, or u square, these are all nonlinear terms. So you will not be able to separate the u from the other parts of the equations. If you can do that, most often it is a linear problem. Okay, in certain nonlinear problems you may be able to do that, but the key signature is u does not appear by itself. It has other terms, dependence on transcendental functions, exponential functions, things like that. And so that's one important classification. Now for linear methods, linear problems, there are a lot of very powerful analytical methods that are available. But for nonlinear problems, no. That's why we need the numerical method. And most of the physical systems are nonlinear. Okay? So we are forced to deal with computer representation of the mathematical model, which is nonlinear. The second type of classification that you should know is steady state versus dynamic. Any idea of how you would describe that? What does a steady state mean?
Doesn't change with time.
Doesn't change with time, right? So if you observe the variable that you are interested in with time, and if it doesn't change, that means that process is operating in the steady state conditions. And they can result in algebraic equations, they can result in ordinary differential equations, they can result in partial differential equations. So next we have to ask, when does it result in an algebraic equation? When does it result in an ODE or a PDE? And that introduces the notion of lumped versus distributed model. Okay? A lumped model says that the variable that I'm interested in has no spatial variations. It's lumped everywhere, it's the same. So if I have a reactor, the reactor is well mixed, I take the composition from one side of the reactor or the other side of the reactor, composition is the same. That would be a lumped model. It would be changing with time. If it changes with time, then I have a lumped dynamic model. If it doesn't change with time, I have a lumped steady state model. Okay? So the distributed ones are ones where there is a spatial variation. Now, if I design a reactor in a lab scale, 0.5 liters, a small one with a very vigorous mixing, then it is reasonable to assume that the compositions are homogeneous, it is well mixed. Based on that, I take my reaction kinetic data, and then I want to design a large reactor, 10,000 liters, because I want to produce more of that particular chemical for which there is a market. Then the question is that large reactor going to behave in the same way as a small reactor in terms of the spatial variation? If I take the sample from the inlet, near the inlet or near the outlet, are they going to be different? Okay. So how do I maintain the same condition that I had in the lab? It's difficult. So if it is difficult, then can I take into account the spatial variation? And in each, so I divide this huge reactor into small tiny reactors, and in each reactor I say the concentration is homogeneous, but it is different from the reactor to the next to it. And they are coupled because one is feeding onto the other. That's essentially, if you understand that concept, that's essentially what CFD is. Okay? You have a partial differential equation, you divide that into tiny cells or grids, and you locally use the concentration rate data and allow for variations in concentrations. So you get more close to realistic situation. Okay? So you should know what is linear and nonlinear, steady state and dynamic, lumped and distributed. You should be able to classify each one of them. Any questions? So this basically notes talks about these concepts that I just introduced. Okay, what is a dynamic model? What is a steady state model, etc. So I have, my apologies, I put this notes late last night, but I will try to put it earlier so that you can print it out and bring it to the class if you like. Now I'm going to take you through a series of examples very quickly. I'm not going to develop these models because, as I said, this is an advanced course. You should be familiar with what I'm talking about. So these examples are just to illustrate the various classifications that we have seen and will set the stage for us to launch and develop the tools that we need, numerical tools that we need. So here is an example of a reactor for methanol production from carbon monoxide and hydrogen. So I have introduced a lot of symbols in describing that particular process. That is the process of developing a mathematical representation for a conceptual problem. The conceptual problem here is you have a reactor and you have a condenser, a separator. And you are putting in carbon monoxide and hydrogen, you are producing methanol. So they react in the first reactor, and what comes out is a mixture of hydrogen, carbon monoxide, and methanol. You can see by looking at the data that the conversion is not very high. Oops, what happened? Did I lose the screen? Oh, there it is. Okay, so the conversion is not very high. So I need to condense that methanol out and recycle the reactants so that I get effectively better yield. So in looking at all these symbols, a lot of data are given to you, and R, the recycle rate, is an unknown, and P, the product rate, is an unknown, and X and Y, the rates of carbon monoxide fed and hydrogen fed, is not known. Okay? So how do I find these four unknowns? Okay? That's the process of mathematical model building. So what I'm going to do is use conservation laws. Okay? Here, mass conservation. So I'm going to write a balance on carbon. I'm going to write a balance on hydrogen. I need to write four equations because I have four unknowns. Okay? And then I can ask the question, is that equation, conservation law based equation, linear or nonlinear? Okay? So there are a lot of linear algebra concepts that we can review using this particular example. Okay? So you understand the very first equation, x plus 0.302 plus 0.004 r equals this. So x is a carbon that is coming in, the rate, so many moles per hour, per minute, whatever. And these are the recycle stream that comes in, okay, containing 0.302 and 0.004, one carbon in CO, one carbon in methanol. So add that multiplied by the rate, recycle rate. That is the amount of carbon entering the reactor. That should equal the amount of carbon leaving the reactor. Again, there are three streams, but only two of them have carbon in that. Right? So that is 0.274 plus 0.095 times 275. So you simplify that. Okay? And you do the same thing for hydrogen balance. You get another equation. So second equation, hydrogen balance. You do the same thing on oxygen balance. Okay? And you get another equation. But then, do we have three equations? I wrote one for hydrogen, one for carbon, and one for oxygen, right? On the inner loop, I have three equations. Do I really have three equations? You cannot just do this blindly. You need to be alert, thinking about it. So what do you notice in these three equations? The first and the third are the same, right? So this brings to fore the concept that you must have seen in linear algebra, the idea of linear independence. And we're going to define what linear independence is and develop an algorithm for testing what linear independence is. Okay? So, but in this case, we really have only two independent equations. The third equation is, in this case, exactly the same, so you could see it. But sometimes what will happen is it will be disguised. The three equations will have all three numerical coefficients. But what you can do is, by taking the first equation, multiplying it by a constant factor, and adding it to the second equation with a different factor, can combine them in such a way that you produce the third equation. Then also, they are linearly dependent. So that is the notion of what linear dependence is. Okay? And you do go through the same process, and you write two more equations for the outer balance. So you end up with 5 equations in total. And you can put these 5 equations in a vector matrix form. Okay? So there are 5 equations, 5 rows, but there are only 4 columns because there are only 4 unknowns. Okay? And can you solve that problem? Is it well posed? 5 equations, but only 4 unknowns. Okay, normally what would you expect? You would expect the number of equations, number of unknowns to be the same, matched. Okay, but we already know that in this one, the first and the third are the same. So if we can throw that out, then you'll have 4 equations and 4 unknowns, and it will be a well-posed problem. What I've shown here is, in fact, use the fact that x is equal to p. If you look at the fourth equation, x minus p equal to 0. So x is equal to p. So you can use that to eliminate one of the variables, and you can condense this 5 into a system of 3 equations with 3 unknowns, x, y, and r. But x is the same as p, right? So you actually know what p is also, even though it doesn't appear in that equation. This is a very simple example, okay? And I can give you an example with a pipeline network with hundreds of pipe elements. You'll have a 100 by 100 system, okay? And I can give you a differential equation where we need to discretize that, and you get a million by million equations, okay? So in the whole hierarchy of models, the linear algebra is the most basic one. You need to understand that, because every problem, whether you're solving partial differential equations, whether you're solving a large set of ordinary differential equations, even nonlinear algebraic equations, you reduce it eventually to having to solve a set of linear algebraic equations, often repetitively. Okay, so this is at the core of entire numerical analysis. So a whole course can be given on how do we solve this in a most efficient way, particularly when the number of equations is on the order of 100,000, million, 10 million, 100 million, whatever. Okay. How many of you know how to solve that equation? Can you give me some of the algorithms that you might have seen in linear algebra? Gaussian elimination, right? Are you all familiar with Gaussian elimination? No? We will go through the basic ideas behind Gaussian elimination very quickly, and there are other methods called iterative methods, and we should know and appreciate the difference between what is called a direct method and an iterative method for solving set of large set of linear algebraic equations. The other thing that you need to know is if there are specific structures in the matrix, you can take advantage of those structures, developing specific algorithms. Because what does Gaussian elimination do conceptually? It eliminates one variable at a time. Okay, so you can, for example, make a linear combination of the first 2 equations to get rid of x from the second equation. In this case, it's already 0. X doesn't appear in the second equation. The second equation is y plus 0.70 to r equals this, right? And the third equation has x. So you say, okay, I'm going to go to the third equation and get rid of x. How can you do that? You can do that by making a linear combination of the first and third. For example, I take the first equation multiplied by 2 and then add it to the third equation, right? And that will make this term 0. And replace it in the third equation. First equation remains the same, but I'm taking the first equation, multiplying it by 2, adding it to it, so that I make this 0. Okay? Then I continue this process. So the Gaussian elimination as an algorithm is only few lines code, but it can solve 100,000 equations using the same idea. Okay? So then you go to the next equation there, and you want to get rid of y. Okay, so you want to make this matrix into an upper triangular matrix. That's what Gaussian elimination does. The structure of it is changed in such a way that every term on below the diagonal is made to 0, is eliminated. Gaussian elimination. Okay, so you can take, you will have a different set of numbers here because you have changed it already. Okay, but you find out what number there is, multiply that by that number, make a linear combination, make that equal to 0. When you are doing that, of course, this will not remain 0. Okay? If you are continuing to do that, and in the last term, you end up having a 0 on the diagonal, what does that mean? It's singular, right? That matrix is singular. It's determinate. So we need to review these concepts of, you have seen it, but you have probably forgotten it. So we need to review what does it mean when the determinant of a matrix is 0. What is a determinant? How do I calculate the determinant? Again, these concepts have been developed and codified into MATLAB. MATLAB, on any other language, you'll have a set of libraries, math libraries, that will allow you to calculate these. But you should understand and never forget. If you're going to be in the business of doing mathematical modeling, you cannot afford to forget these concepts. Okay? So is it steady or dynamic? There is no time dependence, right? That there are 4 variables we identified, x, y, p, and r. None of them depend on time, so it's a steady state. Is it lumped or distributed? Lumped, because there is no spatial variation. Is it linear or non-linear? It is linear. The reason is this matrix coefficients are all constants. Okay? If you have a model where you cannot nicely express this as a matrix with constant coefficients multiplied by a vector equals a constant, then it is not a linear system. So often when you have a nonlinear system, you will not be able to do that. And we'll give you few examples of what nonlinear systems look like. So any questions on this? No? Everything that can go wrong goes wrong. What is the problem with the network connection? Okay. Well, I've heard about self-healing networks. We had a demonstration of that. Okay, so the second example, again from chemical engineering, is a flash drum. What is a flash drum? Petroleum engineers also must do these type of calculations. You have a feed that is coming in at a certain rate f with a certain composition of a mixture, multi-component mixture, and certain temperature and pressure. You just dump it into the drum and control its temperature and pressure such a way that you produce some of them in the vapor stream and some of them in the liquid stream. Okay? So you produce 2 streams, vapor and liquid, with different compositions. So you can control the temperature and pressure to produce, for example, if your goal is to produce 50% as vapor, you can do that. But you need to find what the temperature and pressure should be that will give you 50% vapor and its composition. So there is a model based on conservation laws coupled with phenomenological model. So this is a good example where we combine both. And this is in the notes. I'm going to put the whole chapter 1 on Moodle today. And the development of these equations are in there. I want you to study them. But here I'm just giving you as a case study of a number of examples. So we combine mass balance equation with equilibrium information, which says that the composition Y in the vapor phase is equal to a constant K times the composition in the liquid phase. There is thermodynamics that dictates that these 2 compositions are related, okay, because they are under equilibrium condition. So by using that set of, if I have 10 components, I have 10 mass balance equations, 10 equilibrium equations, say 20 equations. I eliminate all the intermediate variables, just like I do in Gaussian elimination, but analytically I do that, and I reduce it to a single equation and a single unknown. And this equation is called the Rice-Rashford equation. It has a lot of symbols in it, so we need to understand what those symbols are. Zi is the feed composition, which is known, okay, and Ki are the equilibrium ratios. And if you know the temperature and pressure, you know what K's are. Okay? So in a specification, if I give you temperature and pressure of this flash drum, immediately I go and calculate all the K values, and they are known. So the only unknown in that equation is psi, okay, the vapor fraction. So I have one equation in one unknown, but I can look at that equation as an equation in also unknown in T or P. So I have basically 3 variables I have introduced. K implicitly a function of temperature and pressure, and psi the vapor fraction. So there are 3 variables. So if you give me any 2 of those, I will be able to calculate what the third is. Aspen, HYSYS, they will do that routinely. Okay. So let's take the case where I know T and P, and I want to solve for psi. Is it a linear problem or a nonlinear problem? It is a nonlinear problem, right? Because I have a summation. So that if there n is 10, there are 10 terms in here. Each one has psi in the denominator. There's no way I can kind of separate it out. So you must use a numerical method for solving this. Okay? That's a nonlinear algebraic equation. It is a steady state lumped model. Okay? Now, if you ask me to say, okay, I want psi to be 50%, that's a legitimate engineering question to pose. what should be, and I say I'm operating the column at atmospheric pressure, what should be the temperature? Can you find the temperature for me? The equation remains the same. All we're going to treat now temperature as an unknown, and we're going to plug in the equations that we have for K. We have one equation for each component of K. Okay? So using that, you should be able to write a MATLAB code that will solve this particular equation for temperature. Okay? Now let me ask you, again, this is a good question for petroleum engineers. Okay? Now I say I want the psi to be equal to 0. And I specify the pressure as atmospheric pressure and find me the temperature. It's also good for chemical engineers. What would that temperature, what would I call the temperature? Psi is the fraction of feed that is in the vapor, and I want that fraction to be 0. This has nothing to do with numerical methods, but physics. So I have a multi-component mixture, right? And I'm asking you, what would I call, this is just labeling, but there's a concept behind it. I want to see whether you remember the concept. Okay? What would I call the temperature where I have the vapor fraction as 0 and the pressure is atmosphere, and I want to find the temperature? What would I call the temperature? What would that experiment do? Would look like in your mind? So I have a mixture of 10 components in a vessel, and it's atmospheric pressure, and initially it is all liquid, and I keep increasing the temperature. Okay, and I want to find that temperature where the first bubble comes up, because that's a vapor. I've given you the clue now, right? Bubble point, right? So the bubble point, the dew point calculations, they are all embedded in this model. If I put psi equal to 1, I get the dew point. And if I make temperature known and pressure unknown, I get the bubble point pressure, dew point pressure. I give you the pressure and ask you to calculate the temperature. So the entire range of PVT behavior of multi-component mixtures is contained in this single equation. So this is an example of a multi-stage column. Okay? So it's a distillation column or an absorption column, and you can develop a model for each stage, schematically represented as 1, 2, and 3, and you have vapor and liquid that are going countercurrent to each other. Okay? So once again, you go through the process of identifying the variables, put the symbols. So L is the liquid flow rate, V is the vapor flow rate, and X0, X1, X2, X3 are all compositions in the liquid phase. Similarly, Y1, Y2, Y3 are compositions in the vapor phase. And the tradition calls for numbering in the particular way. The streams leaving a stage carry the same index. Okay? So X3 is the liquid leaving 3, and Y3 is the vapor leaving 3, for example. And they are in equilibrium. So you have a relationship between X3 and Y3, similarly between X2 and Y2, X1 and Y1, given by thermodynamics. And you have mass balances for each one of them. Okay? So you need to, so you have identified in this case 8, 10 symbols. Okay? 4 compositions, the liquid phase, 4 in the vapor phase, and 2 flow rates. 10 symbols, and then K also as a thermodynamic model. So you write down the mass balance equations, and here I actually go through the argument of how would I develop a mathematical model, what sort of thought process that you should engage in. Okay, so the state variables in this problem, as I said, are X0, X1, X2, X3, Y1, Y2, Y3, Y4, L, and V. And under what conditions L and V are constant. And if there is significant material transfer, then these rates need not be constant. Then I must actually have L1, L2, L3, L4, V1, V2, V3, V4. And these are all done very rigorously in Aspen, for example. But at this stage, all I want to do is get the basic idea of how does the model look like, what is the structure of the model, what classifications would we place them in, so that we develop the appropriate numerical methods. Okay? So if it is dilute, for example, you can assume L and V to be constant, meaning the transfer between the two phases is small. And is it a lumped model or a distributed model? In order to know that, you need to know the state of mixing, how vigorously these are mixed in each stage in the multi-stage process. And we are going to assume that it is a lumped model. the compositions are uniform. And that is a cause of problem. Towards the later part of this course, we will see how we can relax that using CFD, where we track the flow rates variation within a particular stage. And about thermodynamics, we can have a linear or a nonlinear model. The source of nonlinearity often comes from thermodynamics, from reaction kinetics, and from fluid mechanics. Okay? So we will see examples of both. And I left the space so that I could write, but I am afraid to try even writing on this system. So y versus x. And if the data falls on a straight line, y equals kx, the slope is k, okay? Then I would call that as a linear model. But if I find the data to be something like this, okay, then I would have a nonlinear model. But there is still a model that relates y to x, but often the model is nonlinear unless you are dealing with very low concentrations, extreme purity, for example. Then you can linearize that part of the curve and use that as a linear model. Okay. So a mass balance equation on stage 1 would look like this. Okay. The change in composition at one stage multiplied by V is the vapor rate, and that must equal the change in the liquid composition. So you write one for each one of those stages, and then you can simplify them into this form. So you have 3 equations and 3 unknowns. And what I've done here is wherever I had y, I replaced it by k times x, because that is a thermodynamic model. And then I defined a new variable s, which is L divided by kv. Okay, so I've divided all the terms by k times v. And x1, x2, x3 are my 3 unknowns. And these are the 3 equations. There are 3 stages. And the right-hand side typically contains the known quantities. That is the forcing on the system. So in this particular case, Sx0. 0 is an inlet concentration, and y4 is also an inlet concentration on the vapor side. Okay. So once again, I have a system of 3 equations, 3 unknowns. Is it linear or nonlinear? That depends on k. If I assume k to be constant, then s equals L over kv will all be constants. Okay? Then I will get a system of linear equations. What do you see in terms of the structure? It is there are elements on the diagonal, and one row above the diagonal and one row below the diagonal. Can you guys see in the back? Difficult, isn't it? I am not able to figure out how to zoom this. I will figure all this out by next class. It will be much smoother in terms of presentation. Pardon me? Right click? Right click gives you something else. No? This is within the Adobe Connect program. It's a white screen of some sort, and I haven't played enough with it. So it will be a linear equation if k is assumed to be constant, because the matrix T, I'm calling it, is a constant matrix. So x is the unknown vector, and v is the forcing term, and I can solve that. It is a tridiagonal system. So in your Gaussian elimination, you will know that you don't have to work on removing these terms because they are already 0. Okay? So there's a specialized version of Gaussian elimination called Thomas algorithm. And these kinds of algorithms are there for tridiagonal systems, pentadiagonal systems, block tridiagonal systems. So you see some structure, you exploit that structure in developing a specialized version of that, because you don't want to do millions of multiplications involving zeros to eliminate them, right? It's unnecessary floating point operation. It becomes important not when you have 3 by 3 system, but when you have 3 million by 3 million system. Okay. Now, the same example, I've said, okay, now I have, instead of 3 tanks, I have n tanks. N could be any number. Often you will find in a plant, you'll have 50 stages, 100 stages. If you're separating very difficult material like uranium or material that have very close properties, okay, then you really need very large like heavy water production from water. Okay, you'll need hundreds and hundreds of stages to do that separation. So you will have a very large system of equations, but the structure is going to be the same. Okay, the diagonal elements are known, the one above and below diagonal elements are known, the rest are all zero. It's a tri-diagonal system. Okay, so it calls for a specialized way of solving those equations, and we will develop those algorithms. A second variation is, as I said, a linear model versus a nonlinear model. Come on. Okay. So when you have a nonlinear model between y and x, okay, k is now a function of x. So what does that do to these equations? T now becomes a function of x. The matrix T becomes a function of x. So the elements so I write it as T as a function of x multiplied by x equal to b. So you have now a product. You can see there is a matrix that depends on x, and then it multiplied by x. That is a nonlinear term. Okay. So how can one solve such a problem when the matrix itself is an unknown? It depends on the unknown values. You develop an iterative method. So what you do is you propose an initial guess for your x1, x2, x3, x4, xn. Okay. Once you make an initial guess, you verify whether the equation is satisfied. So you plug that into your matrix T and evaluate all these elements. Now T is a matrix with numbers, and multiply that by, for example, assume x and see whether it is equal to b. Okay, it is not equal to b because you just made an arbitrary guess. What do you do next? You find a better guess. How do you find a better guess? You treat this x as the unknown, this as a known based on the guess. Okay, so you just invert that matrix. So x is equal to t inverse times b, but the t was based on a guess. Okay, so you get a new value of x, you take that value of x and put it into t and continue the process. And when you get back as a solution the same vector that you put in, then you have reached converged value. Okay, so that is the scheme for basically nonlinear methods. So here I am indicating that by saying t as x of old, an old value that you assume, multiplied by x new, the new value that you are going to calculate, is equal to b. So x new is equal to t inverse b. And then you repeat that process in a loop until you reach convergence. So that is the basic introduction to how we solve nonlinear problems in an iterative manner. By making a guess and checking whether the guess satisfies it. If not, developing a new guess. Now, in some cases, you might get into a nonlinear situation even when you have k as a linear model. Okay, y equals kx is a linear model is a good assumption, but all I've done is I've changed the specification. Okay, instead of specifying, that is, in the traditional problem, let me go back to this figure. What is that figure? Yeah, in this traditional problem, I know the liquid rate, I know the vapor rate, I know the inlet composition x0 and y4, and I'm asking you to find x1, x2, x3, the exit composition, and once you know that, you know what y1, y2, y3 are from the equilibrium equation, right? Suppose I'm interested as a process engineer in a different problem where I need to take this composition x0 and change it to a given composition x3. Okay, and I still know what is coming in y4. So this would be a classic example of maybe in the gas phase you can relate it better, removing the pollutants from a power plant. For example, you have a lot of sulfur dioxide from the emissions in the power plant, and you want to remove the sulfur dioxide, and you're using a solvent. Okay, so you know y4, and you want to reduce it to y1, a known concentration. Okay, a very small value. So you treat y4 and y1 as specifications, and x0 of course is known, and you know how much of vapor you need to process, how much of gas you need to process v. So you say how much of solvent should I use to achieve this? Okay, so the same problem, the same model, the specifications have changed because I've chosen to exercise my degree of freedom in a different form. Instead of specifying Lx0, Vy4 or the 4 numbers known, I'm saying what I know is V, Y4, Y1 and X0, but I don't know L. When I have that situation, I will have the model looking like this. So the 3 functions, they are nonlinear because I have L as an unknown, which multiplies by Y1, which is an unknown. There are 2 unknowns that are multiplying each other. That makes it nonlinear. Okay? So I'm just trying to illustrate how nonlinearity can appear in a model and how you can detect that kind of a nonlinearity. Okay? So once again, the method of solving these is going to be make a guess, get an improved guess, and continue the process in an iterative fashion. Any questions? The next example is a reactor in series. Okay, so I have a feed which is coming in with a composition of A0, and there is a reaction, an autocatalytic reaction taking place, for example, in reactor 1, which produces composition to A1 that is fed into the next reactor, and so on. So all the compositions A1 to AN are unknown. A0 is the inlet composition, I know that. Feed, I know. And V, the reactor volume, I may know, I may not know, depending on the specifications that I have. So once again, I need to write the mass balance equation for each reactor. I will get one equation, and I will need a phenomenological model that will tell me how fast that reaction is taking place, the rate of reaction. Okay. So here the phenomenological model says the rate of reaction is equal to the reaction rate constant times the volume of the reactor times AI squared. Is it going to be a linear model or a nonlinear model? Nonlinear. Why? AI are the concentrations that are unknown, and I have a square of it. Okay, so that's immediately a nonlinear model. And this is the mass balance equation, which says the rate of reaction, the rate at which the particular reactant is consumed, is equal to the change in the concentration across that reactor. And you will have one such equation for each reactor. And you assemble all those equations, and you get n equations if I have n reaction. Now beta here I have regrouped as a dimensionless number, which is kV over f. Okay, so either I can have k, or I can have v, or I can have f as an unknown, then beta becomes an unknown. But if I know the reaction rate constant from measurements, and if I know the volume of the reactor and the feed rate, then beta is a known constant. So in this equation, beta is known and A0 is known. All the others are unknown. Okay, so because I have AI squared, it makes it into a nonlinear equation. That is a nonlinear equation, lumped, steady state model. So it's an algebraic equation that we need to solve. So a few examples of lumped dynamic models. So I really need to go to the bottom of this. I'm going to be able to do it. Okay. I think those guys are still there. Let me see whether, there. See, sometimes I get this hand, that's what I need to push it. Sometimes I don't understand why it happens. Okay, so here is a model which is going to be an example of a lumped dynamic model. So the process is, I have a crucible into which I pour a molten metal, and I want to let it cool, okay, in some sort of a heat treatment process, for example. And I want to know how does the temperature T1 and T2 change with time, okay, and T infinity is the surrounding temperature. So here I can ask the question, is T1 going to be different from one side to the other side? If it becomes important that the differences are significant, then I need to use a distributed model. Okay, and I will give you an example of a distributed model later. But I'm going to assume, because it is a metal, it has a very high thermal conductivity, that the temperatures are going to be uniform inside the molten metal. Okay, So that's what makes it a lumped model. But it is changing with time. That's what makes it a dynamic model. The same thing for T2. That may not be a very good assumption that T2 everywhere is the same. T2, let me ask you the question. I just said that T2 represents the temperature of the crucible, some sort of a ceramic material that I keep, for example. T1, I argued, is a good approximation to say it is lumped because it's a metal, very high thermal conductivity. In T2, if I take the temperature at this point and at this point, will they be the same? You would expect them to be very similar. But if I take the temperature close to the inner one, close to the outer one, would you expect them to be the same? That kind of an intuition you need so that you can develop the model correctly, because the temperature gradient is going radially out, for example. Okay? And because the crucible may not have a very good thermal conductivity, it may not be a good assumption to say that it is homogeneous, it is lumped. But we are going to make that assumption in this case, keeping in mind that that may be the weakest point in your model. Okay? Any questions? Am I going fast? Which I always do, I guess. No? That's good. So you write an energy balance equation this time, one for your control volume with only the molten metal as your control volume. The second energy balance equation you write with only the crucible as your control volume. So identify what flux of energy is there from one control volume to the other control volume, and you can get the equation for example, rate of change d dt of m1 c1 t1. That is the energy content in the molten metal. Okay, and that is equal to molten metal doesn't have any source of energy, so that's zero. Input minus output, but the input is zero, and the output is the energy that is lost from the molten metal to the crucible. Okay, so that is going to be modeled as the heat transfer coefficient times the area times the driving force, which is T1 minus T2. So T1 is the temperature of the molten metal, which is an unknown. Okay, and similarly T2 is the temperature of the crucible, which is an unknown, but both are changing with time. So I have one equation here, mass is known, Cp is known, H1 is assumed to be known, the heat transfer coefficient, and the interfacial area is assumed to be known. Okay, then you do the energy balance on the crucible, the same thing, ddt of m2 Cp2 T2, which is the energy content in the crucible at any time, equals heat into the crucible, which is coming from the molten metal. So that term is the same. These two terms are the same. Okay, and then minus the heat that is lost to the surrounding, which depends on that temperature gradient, T2 minus T infinity. So you have two equations and two unknowns, but you end up with an ordinary differential equation. So this ordinary differential equation can be put in a vector matrix form, where theta is your unknown vector consisting of T1 and T2, and A is your, now is this problem linear or non-linear? T1 and T2 are the unknowns, and they appear by themselves. All the products of that are constants, they are known. Okay, so that is a linear model, and if it is a linear model, you can write it as equal to A times theta plus B. A is a matrix of numbers, and B is a vector of numbers. It will be a 2x2 system, two equations and two unknowns. T1 and T2 are the two unknown functions that we want to find. So here I've defined what theta is. Theta is the vector T1, T2, and A is the vector consisting of coefficients from those two equations. Okay, and B is the forcing term. Now if the left-hand side of this equation is equal to 0, d theta dt equal to 0, what will you have? You'll have an algebraic equation. When will that be valid? Under steady state, right? This will reach a steady state. When we reach steady state, this will be equal to 0. Then if you want to find the temperature theta under steady state, what will you do? Just solve the A theta plus B equal to 0. So move the B to the right-hand side. So theta is equals minus A inverse B. You know A, you know B, you can calculate that. Okay? But to get the entire transient history, you need an initial condition. Theta at time equal to 0. what is the temperature of the molten metal, what is the temperature of the crucible. Here I'm saying Ti is whatever the temperature of the metal is, and the crucible is at room temperature, T infinity, for example. So that's an ordinary differential equation, linear, and we need to develop a whole class of methods for solving those kinds of problems. And a second example in that category is the ozone decomposition in the atmosphere. And there are two reactions that are written, O3 plus O2 equals O plus 2O2, and then O3 plus O equals 2O2. It's a model for a reaction mechanism for how ozone is depleted in the atmosphere. Okay. Here we are assuming that it's homogeneous everywhere in space, okay, which is not true. We know that ozone holes form in certain regions, right? So there is a variation in the concentration. So this is a lump model, and there are very sophisticated models for ozone depletion with 100 reaction mechanisms, hundreds of equations. So this is one of the simpler ones. The reason I chose to do this is from one of the papers. I might give this as on a problem project. Okay, so we have two equations in two unknowns representing the two chemical reactions. Okay, and the equations are written as dy1 dt equals some function on the right hand side, depends on the reaction rate mechanism model, and epsilon times dy2 dt equals some expression on the right hand side. Okay, the reason I picked this example is epsilon is a constant and kappa is a constant. There are two parameters appearing in the problem related to the rates of reaction. Okay, and there is some initial condition that needs to be given. But typically epsilon, for example, turns out to be 1 over 98. It's a very small number. Okay, and kappa is 3. When epsilon becomes a small number, what happens to the second equation? It becomes an algebraic equation, right? You can assume, that's an assumption, if dy dt is of order 1, then you're taking that and multiplying it by epsilon, so it's almost close to 0. I can set that equal to 0. Something that we have seen in fluid mechanics course. A number of you have taken that from me, right? At that time, I mentioned this kind of a thing happening in reaction engineering. Do you remember what it is called? In fluid mechanics, we would call that as boundary layer theory, right? A differential term multiplied by a small coefficient, viscosity, for example. When we say the viscosity is 0, then we throw out the viscous term completely, and we get the Euler equation, right? So here we are saying that epsilon is close to 0, so we are going to throw that term out. We can never do that, but we tend to do it because it simplifies the analysis, and this is called the quasi-steady state approximation in reaction kinetics. What does quasi-steady state approximation mean? It means that there are two reactions. One reaction is occurring so fast, okay, it always reaches equilibrium. Okay, so that's why it's quasi-steady state. The other one is not steady state. It is dynamically changing, but one is fast enough that it is always under equilibrium conditions, so you can set that equal to 0. Okay? These are called differential algebraic equations. Ronald will tell you an example on how to solve these, right? COMSOL, you can do that, right? DAEs, differential algebraic equations. They occur often in engineering problems. This is one of the examples, okay? Here is an example I think Mrinal is going to also show you, which is a reactor. Okay, it's a CSTR, and there is a paper that was published in 1950 exploring the dynamics of this equation. So there is a mass balance equation and there is an energy balance equation. So it's a non-isothermal reactor. Okay, and so there is heats of reaction term. Okay, and there is a reaction itself, the conversion. So there is a heating jacket or cooling jacket. Here it is. So there is temperature from the reactor into a cooling jacket. And these are all the parameters in the problem. The unknowns are A and P. Okay? And this is a fascinating problem because it exhibits a lot of multiplicities and stability issues that we are going to discuss later on in this course. So by setting this equal to 0, you can get the steady state concentration and temperature of the reactor. Okay, but if you put a perturbation, what does that do to the steady state? And as you change the parameters, the cooling, for example, the cooling temperature, how does the dynamic change? Okay, these are the issues that one can deal with. So again, it's an example of a lumped dynamic model, ordinary differential equations. So in the remaining 5 minutes or so, I will show you the distributed steady state and distributed dynamic model. So this is an example of a heat exchanger mounted with a fin. So there is a base plate which is at a very high temperature T0, and the goal is to dissipate the heat as effectively as possible. You have this in automobiles, you have this in CPUs, okay, these fins to dissipate the heat. So how do we analyze the efficiency of a particular fin? How do we design a fin with this particular geometric configuration that optimizes? When I say optimizes, you need to have an objective function. So you want to maximize the heat transfer while minimizing, for example, the amount of material that you used, the weight, for example. Okay. So what you do is you recognize that in such a case, the temperature close to the base is going to be different from the tip of the fin. So it is a distributed model. There is significant spatial variation. We cannot avoid that. But I can say that this fin is operating under steady state condition. Then I will get a steady state model. Then I can ask what happens if I'm just starting it up. Then I have to include the dynamic one. So initially I'm going to assume steady state. So the accumulation term is 0. And on the right hand side I have a differential element that I take. Because it is varying in space, I take a differential element. And that is my control volume. So the flux coming in, the flux going out, and the flux going out from the top to the surrounding. So those are the three fluxes of heat into that control volume. So Q times A is by conduction on the left phase of X. Same thing at X plus delta X on the right phase. And this is the heat transfer to the surrounding in terms of the heat transfer coefficient. And then you take the limit process, etc. You end up with an ordinary differential equation. It's a second order ordinary differential equation. The unknown here is T, the temperature. Everything else is known. H, the heat transfer coefficient. P, the perimeter of the thing. A, the cross-sectional area of the fin. K, the thermal conductivity are all given. So when you have a distributed model, you will always end up with a differential equation. Okay, in this particular case, it is a second order equation. So you need two boundary conditions. One at the base of the fin, x equal to 0. The other one at the tip of the fin at x equal to L. And at the tip of the fin, there are two possibilities. So boundary conditions come from the physics, from understanding the physics. So one is to say that the tip is as cool as the ambient temperature, it's T infinity. The other one is the tip is so thin that the flux of energy out is equal to 0. Okay, but the tip could be hot, and I don't know what the temperature is. So that's a well-posed problem, a second order equation with two boundary conditions, a couple of variations on the boundary conditions. We will see how to solve each one of those variations. Is it linear or nonlinear? It's linear. Why is it linear? Because the unknown is T. Unknown is the temperature of the temperature distribution as a function of x. T as a function of x. Okay. So if I say K is a constant, then it is a linear problem. Now A could be varying as a function of x. Does that make it nonlinear? A is the cross-sectional area of the fin, and I have shown it here. It is tapered fin, so the cross-sectional area is actually changing. If I say A is a constant, then I will have basically a uniform thickness fin. Okay, but I could have A as a function of x. So if I specify that A is a function of x, my question is that a linear problem or a nonlinear problem? Still, it's a linear problem. Okay, when we do this discretization, you will see what happens to the matrix. Okay, in one case the matrix will have constant numbers. In the other case, all same numbers in a particular row if the thickness is uniform. But if the thickness is non-uniform, you'll still have numbers, but the numbers will change from element to element. Okay, but how can I make this a nonlinear problem? When would nonlinearity become important? Yeah? If K depends on temperature itself. Okay, the thermal conductivity depends on temperature, and many materials do exhibit that property. Okay, then I need to get that information and put it here. Then it becomes a nonlinear problem. So this particular example we will take and solve it in all three cases to see how we handle linearity versus nonlinearity in solving it by finite difference method, finite element method, method of weighted residuals, and stuff like that. This is the continuing on the same problem. Once you get the temperature profile, as an engineer, you are interested in answering practical questions. That is, how much of heat is this fin going to dissipate? Okay, you need to know what is the total Q. And you can calculate that by one of these two ways. Either by calculating how much of energy is entering the fin at the base of the fin, okay, by knowing the temperature gradient. Now that you know the profile, take the gradient multiplied by 8, that will give you the Q. Or by tracking how much of energy is lost from the surface of the fin to the surrounding, so that will be an integral evaluation. So you can evaluate the same quantity either by derivative or by integral. So we will have the need to evaluate numerical differentiation, numerical integration, etc. That's one way, in fact, of checking the accuracy of your solution. These two numbers should be the same. Calculated differently, but they should be the same. And the last example is the same problem, but now I have transient situation. This is a case where I'm just starting up the engine is heating up, so the base temperature is changing with time. Then the questions like how long does it take for it to reach a steady state can be answered by solving this equation. The right hand side of this equation is exactly the same as before, and the left hand side is your accumulation term. Okay, and that's a partial differential equation. Okay, and it needs one initial condition and two boundary conditions, so they are identified here, and it's still a linear problem because t is the unknown that appears by itself. It doesn't have any nonlinearity in the term. So that's a very quick survey of the concept of lumped, distributed, steady, dynamic, linear, nonlinear classifications. I've given you one example of every kind. We didn't develop it in detail, but I just gave you the structure of the equation so that you understand a little bit about the physics and be able to identify what type of a model that is. And this is all in the chapter 1 of several chapters that I've started writing as a book, but I never got around to finishing it. But I'm going to put that on the Google Docs and Moodle so that you will have access to it. You will see there the development in greater detail. And at the end of this chapter, you will see a lot more examples, about 20 other examples coming from different applications, from some from bio, etc. So the next lecture, we are going to start with linear algebra, reviewing some of the linear algebra notations and stuff. I want to know what your background is. So I'm going to ask you a series of quick questions. How many of you have heard of Gram-Schmidt procedure? 1, 2, 3. Okay. How about Wronskian testing for linearity? Okay. Okay. Determinant, of course, you know how to calculate it. Okay. Gaussian elimination, successive over relaxation. You're going to be bored for a while, I can tell you. Okay. I need to lay those foundations though for the rest of the class. Only a few hands just went up, so we will review those material in the next maybe 2 lectures, and then move on to solving nonlinear algebraic equations. That will be our starting point for this course in real-time sense. And Mrinal will show you some of the computational parts. Right? We have to schedule those. Okay. Any questions? If there is anything that you would like me to consider including in the course, so that you are expecting to learn something, I would like to know. Okay, so that I can at least tell you, well, you will learn this, or see whether I can fit it in, or maybe you are wasting your time unless you are just filling this for a course requirement. Okay, so we'll see you Monday to Wednesday. I know some people have difficulty at this time, but if I will try to figure this out. If this works out, you would be able to attend this lecture from your office. Question? Pardon me? Oh, is it? Oh, so Monday is a holiday. Okay. My apologies. Then we meet next Wednesday. That gives me some breathing room to catch up with these technologies. Thank you.